Principles of Thermal Processing of Milk. Good morning, students. In today's lecture, we will go deeper into the scientific principles behind thermal processing of milk. Previously, we understood why heat treatment is required. Today, we focus on the kinetics, the mathematical and microbiological principles that govern microbial destruction. Let us begin with the concept of microbial destruction by heat. Heat is applied in a specific time-temperature combination. This leads to microbial death through denaturation of proteins and enzymes. When proteins inside microbial cells denature, cellular metabolism stops, and the organism cannot survive. The final outcome is safe milk, pathogen-free, and shelf-stable. Additionally, heat inactivates enzymes, extends shelf life, and ensures public health safety. Microbial death follows a logarithmic pattern. Bacteria do not die instantly. They die at a constant rate under constant heat exposure. This is called log linear order. The 90% rule states that in one d-value time, 90% of the remaining population is destroyed. When we plot log survivors versus time, we obtain a straight line. This indicates exponential decay. Mathematically, n is equal to n naught multiplied by 10 raised to power minus t upon d. This slide presents first-order kinetics. The rate equation is dn upon dt is equal to minus kn. Here, dn upon dt represents the rate of change in population. The negative sign indicates reduction. K is the rate constant, which depends on temperature. Higher temperature increases K, meaning faster microbial death. The integrated form is ln n upon n naught is equal to minus kt. This explains why the survivor curve appears linear on a semi-log graph. Let us analyze the rate of microbial inactivation. As temperature increases, the slope of the survivor curve becomes steeper. Steeper slope means higher death rate. This is the temperature-rate relationship. The Z-value concept explains temperature sensitivity. Z-value is the temperature increase required to reduce the D-value by 90% or 1 log cycle. The Arrhenius relationship describes how rate constant K depends exponentially on temperature. Thus, small temperature increases can cause large increases in microbial destruction. In practical situations, survival curves may show non-linear patterns. First, shoulder effect. There is an initial lag before death begins. This may be due to cell repair mechanisms or cell clumping. Second, log linear phase. This is the ideal first-order destruction phase. Third, tailing effect. The curve flattens at the end. This indicates resistant subpopulation or protective effects. Understanding these patterns helps in accurate process validation. Let us understand the log survivors versus time graph. Decimal reduction time or d-value is the time required at a specific temperature to reduce microbial population by 90%. The slope of the line is inversely related to the d-value. Slope is equal to minus 1 upon d. A steeper slope means a smaller d-value, which means faster microbial death. For example, if population drops from 10,000 to 1,000 in 5 minutes, the d-value is 5 minutes. This forms the basis of process calculations. The importance of kinetics in dairy processing is significant. For pasteurization safety, the target organism is Coxiella burnetii, the most heat-resistant non-spore former. The goal is complete elimination of pathogens while minimizing nutrient loss. For commercial sterility, the target shifts to bacterial spores such as Clostridium botulinum. Process engineering uses D and Z values to calculate holding tube length, design heat exchangers, and ensure turbulent flow. Validation requires 5 log reduction, which equals 99.999% destruction, and verification tests like alkaline phosphatase test. This slide presents a visual summary. Thermal processing begins with a heat source, plate, or tubular heat exchangers. Microbial inactivation follows first-order kinetics. Critical parameters include D value, time factor, Z value, temperature factor, F value, total lethal effect. Methods include LT-LT, 63 degrees Celsius for 30 minutes, HTST, 72 degrees Celsius for 15 seconds, UHT, 135 degrees Celsius for 2 seconds. The ultimate goal is balancing safety with nutrient retention and sensory quality. To conclude, microbial destruction in milk follows first-order kinetics. D, Z, and F values are essential parameters for designing safe thermal processes. The objective is always to balance pathogen destruction with preservation of product quality. Understanding these principles is fundamental for dairy engineers and quality control professionals. Thank you.